Okay. Good morning, students. Today we are in the continuity of the flywheel and flywheel designs and flywheel application in the punching press. So previously we have discussed about the flywheel. What is the purpose of we know that the flywheel is like a reservoir, or otherwise, the flywheel used in the machines. It just serves as a reservoir which stores the energy during the period when the supply of energy is more than the requirement, and it releases it during the period of when the requirement of energy is more than the supply. So, and at the same time, the coefficient of fluctuation of speed and coefficient of fluctuation of energy also. The fluctuation of speed is nothing but the differences between the maximum and minimum speeds during the cycle of period is known as the maximum fluctuation of speed, and the ratio of maximum fluctuation of speed to the mean speed is nothing but coefficient of fluctuation of speed. Then we know the formula of the coefficient of fluctuation of speed as Cs is equals to n1 minus n2 by mean speed, that is n. And at the same time, coefficient of steady lines, that is the reciprocal of coefficient of fluctuation of speed. Then at the same time, that is the energy stored in the flywheel. So that is the concept we know in the previous class. Finally, we have get it the equation as delta E, that is maximum minus minimum kinetic energies. The formula is 2E Cs, that is 2 into capital E into Cs, coefficient of fluctuation of speed. So finally, here it is the dimensions of the flywheel, which is need to be designing while preparing any flywheel. How much of energy is to be stored is depending on the design of the flywheel. So, what is the design means? Let us consider a rim of a flywheel, that is the diagram which shows the flywheel design. In that, let capital D be the mean diameter of the rim and capital R be the mean radius of the rim. And A is the cross-sectional area, and that is rho is the density of the rim of the material, and n is the speed of the flywheel. Omega, that is angular velocity of the flywheel, we can directly find it out by 2 pi n by 60 formula, and v is the linear velocity at the mean radius. So the mean radius with the angular velocity, that is omega into capital is equals to the final formula, we can get it with the linear velocity. And what is the tensile stress, that is a sigma tensile stress, or we can call it as a hoop stress, that is due to the centrifugal action of the force. Then here we are considering a small element in the rim. We can observe in the df, that is let it be its substance an angle of delta theta at the center of the flywheel. So that a small portion is to be enough to calculate the entire energy stored or dimensions of a rim or a flywheel. Then in that, due to the volume of a small element, that is A into R delta theta, and the mass of the small element is mass is equals to density into volume. So rho into AR delta theta, and the centrifugal force of the element which acting radially outwards, due to that, that is df is equals to dm into omega square into r, that is equals to rho a r square omega square into delta theta. So with that, the vertical component is also is to be find out the vertical component of a df, that is a df sine theta, rho a r square omega square sine theta into delta theta. So finally the total vertical upward force which is tends to burst the rim across the diameter of the xy, which is called uh, it is across the dimension is xy. We can see it in the screen. The vertical upward force is to be calculated as 2 rho a r square omega square, and the vertical component upwards will be produced as the tensile stress or hoop stress, is also known as a centrifugal stresses, which are circumstantial stresses, that is to be resisted by 2p. Actually, these are upward, which is in the opposite direction, that we can see in the diagram, that is p. P is which is acting downward uh, about the center of xy in the two positions. So we calculate it as 2p. So for that, the 2p is equals to 2p is nothing but the force, so rho a. By equating 1 and 2 equations, we can get it the thing as 2 rho a r square omega square. That is the first equation, which is to be equivalent to the upward total force, it is a centrifugal stresses, so 2p. So both are the conditions as same. So for that we are equating equation 1 and 2. 2 rho a r square omega square is equals to 2 sigma a. So 2 cancel and a cancel. So finally we get it sigma is equals to rho r square omega square. So r omega we call it as linear velocity, that is sigma is equals to rho v square. Then v, if the linear velocity is equals to root of sigma by rho. So this is the final content we are getting that. So we know the mass. So actually, what we need to measure is the dimensions of the rim. Dimensions is nothing but the what is the mass and weight or mass of the rim, and dimensions is size. Okay, diameter, how much of diameter or how much of breadth or thickness of the rim. So that is the thing we need to find out. We know that the mass of the rim is equals to mass is equals to volume into density pi dA into rho. Then A area is equals to pi d m by pi d rho. By equating these two equations, uh, from these that is third and fourth, we can find out the value of the mean radius and the cross sectional area of the rim. If the cross sectional area of the rim is rectangular, then area is equals to breadth into length. Actually, the flywheel size or shape, it may be circular or rectangle. That is depending on the application. So, if the cross section of the rim is rectangle, then area we will call it as a B, that is a width and thickness. Okay, then that is the area we need to calculate. Then coming to what is the flywheel for punching press. The flywheel, we know that the case, and what is the punching press. So we know that the function of a flywheel or application of flywheel in an engine, which is reduce the fluctuation of speed. So when the load on the crankshaft is to be maintained at a constant, and input torque varies during the cycle. The flywheel can also be used to perform the same function when the torque is constant and the load varies during the cycle. Such an application is found in punching press or in a riveting machine. So a punching press is shown like an figure, and the crank is driven by another motor which supplies the constant torque, and the punch is at the position of the slider in a slider crank mechanism. So from the figure we can see that the load acts only during the rotation of the crank, that is a rotation, that is theta, what we represent here. Theta is equals to theta 1 and theta 2, that is the angle of motion of the crank. When the actual punching takes place and the load is 0 for the rest of the cycle, unless the flywheel is the used, and the speed of the crankshaft will increase too much during the rotation of the crank from reverse direction of theta 2 to 2 pi, or theta is equals to 0 from, and again it will go for from 0 to theta 1, because of there is no load while the input energy continues to be supplied. On the other hand, the drop off in the speed of the crankshaft is very large during the rotation of the crank from the constant to due to much more load than the energy supplied. Thus, the flywheel has to absorb the excess energy available at one stage and has to make up to the deficient energy at the other stages to keep up the fluctuation of speed within a permissible limits. This done by choosing the suitable moment of inertia of the flywheel. Then, what is the energy is to be required for a punching a hole? So that is, if this energy is determined by the size of the hole punched. That means how much of size of the hole is to be required. With that, the amount of energy is to be required to punch the machine. So, and what is the thickness of the material and the physical properties of the materials also. These are all the things we need to note it down while calculating the how much of energy is to be required for punching a hole. So further, we are taking that let D1 or D be the diameter of the hole to be punched for a metal plate of the thickness T. With that, the shearing area, that is A is equals to pi d into T. If the energy or work done or sheared force is given, the work done per hole is work done per work done into sheared area per hole. As one hole is punched in every revolution, work done per minute is equals to work done per hole into number of holes to be punched in a minute. So how much of power of motor is to be required means power is equals to how much of work done per minute by 60. That means we can calculate it for seconds also. So the excess energy is to be stored by the flywheel. E is equals to E1 minus E2. That is the that is maximum fluctuation of energy. That is energy differences. So where E1 is the energy required per hole, E2 be the energy supplied during actual punch. So E2 is the supplied energy supplied per second into actual time of the punch. So based on that, we are taking the problems also here. So apart from these, we need to do some more thing. We need to know that is maximum shear force is to be required for punching is sheared area into unlimited or ultimate shear stress, that is pi dt into tau. Okay. It is assumed that if a hole is punched, the shear force decreases uniformly from maximum value to 0 then the work done per energy is to be required for punching a hole is E is equals to half Fs, that is shear force into the thickness. So these are the things we need to know about the thing. When a single cylinder, the problems on turning moment diagram and the flywheel, okay, and then a single cylinder, single acting four-stroke gas engine develops 20 kilowatts at a speed of 300 rpm. The work done by the gases during the expansion stroke is 3 times the work done on the gases during the compression stroke. So we are considering a single cylinder, single acting four-stroke gas engine. How much of power is delivered means P is equals to 20 kilowatts at a speed, it is N is equals to 300 rpm. Up to now it was clear. Then here it is a major important condition is that the work done by the gases during the expansion stroke is 3 times the work done on the gases. So we have to note a underline the thing as work done by the system, work done on the system. So by the system and on the system, both are some variation is there. So we have to keep a reminder that on the system or by the system. Okay. Then by the system is 3 times the work done on the system, okay, during the compression stroke. Okay. First strokes being negligible. Why these are negligible means in the condition itself, the problem itself they have given the condition, but we know the theory or while deriving the function of turning moment diagram for single acting during the suction there was no energy is to be developed, only the energy is to be supplied. So if the total fluctuation of speed is not to exceed plus or minus 2% of the mean speed and the turning moment diagram during the compression and expansion stroke is assumed to be triangular in shape. Find the mass moment of if the total fluctuation of speed is not to exceed plus or minus 2% of mean speed and the turning moment diagram during the compression and expansion stroke is assumed to be triangular in shape, and find the moment of inertia of the flywheel. So here the profile or turning moment diagram shape is triangular shape. One thing is clear. And one more thing is the fluctuation of speed, total fluctuation of speed is not to exceed plus or minus 2%, okay, of the mean speed. So write down the given data, power 20 kilowatts, so converted to watts 20 into 10 to the power of 3 into that is N also we have given N is equals to 300 RPM. Therefore, omega is equals to 2 pi n by 60. So, in every problem during the turning moment diagram, whenever the speed has given, you can directly calculate the omega also at the same time. So, it is very easy to substitute the omega value in the further. And next, what is the last one? Since the total fluctuation of speed, that is omega 1 minus omega 2, is not to exceed plus or minus 2%. So, every time you just to be clear that whenever in any problem it has given that plus or minus 2, you just double it. Okay, so total fluctuation of speed is omega 1 minus omega 2 is equals to 2%. He has given, you just double it, that is 4% of mean speed. Mean speed notation is omega. So omega. Then after that, coefficient of fluctuation of speed. CS formula is omega 1 minus omega 2 by omega. So substitute these thing as omega 1 minus omega 2 as 4%, that is 0.04. That is the thing he is to directly substituting for the functioning of the problem. So the turning moment diagram of the crank, he has given that it is a, as shown in the figure, it is assumed to be in a triangular. So every time we have to given a diagram as triangle wherever it is required. It is only during the compression and expansion stroke. Since in the question itself, it has given that during suction and expansion it is negligible. Okay, and at the same time he has given that the only compression and expansion, sorry, the suction and exhaust strokes are negligible. During compression and expansion strokes is assumed to be triangular. So only no need to draw a diagram during the suction and exhaust. So but we have to differentiate where the suction, how much of the crank angle for the suction and compression and expansion and exhaust. So just draw a graph, that is vertical axis and horizontal axis. The vertical axis called a turning torque. Okay, torque mean at the maximum, and horizontal is a crank angle. That is a crank angle and turning moment. So we know that the four-stroke engine and the number of strokes per cycle is n is equals to speed by 2, half of the speed. That is p is equals to 300 by 2, 150. Then work done per cycle is p into 60 by n. So that is the formula we have already discussed in the single stroke, single cylinder, four stroke engine. Okay, there we can, from there we have to collect the formula for number of working strokes per cycle and work done per cycle. Okay, p into 60 by n. There we have getting the n value 20 into 20 into 10 to the power of cube is the power into 60 by n, number of working strokes is 150. So finally we get it as 8000 Newton per Newton meter. So this is the work done. Since these are the diagrams during the section, so in the same way, we have to differentiate the segregation of the crank angle also, that is section. Okay, by taking of the default four-stroke engine diagram, there you can see that the crank angle position for suction, compression, and expansion and exhaust, that is pi, 2 pi, 3 pi, 4 pi. Then the diagram is compression. Compression diagram is there is no work done by the system. So it has to be making a triangle already mentioned in the thing. So triangle, it is to be some energy is to be required. So it has mentioned in the expansion. After compression, we are going for expansion. Meanwhile, there is a difference between compression and expansion. There is an ignition will be or working stroke will be there. So there with the working stroke, there is a large of amount of energy will be delivered. With that, the remaining all the process will be continued. So what how much of energy is delivered? That is we have to be calculated. That is T excess. Since we have given that the work done during the suction and exhaust strokes is negligible. Therefore, the net work done per cycle is during the compression and expansion strokes only. So, WE minus WC is equals to WE minus W by 3, where the exhaust stroke or the expansion strokes is 3 times the compression stroke. So W is equals to 3 WC. We just substituting that we can get it 2/3 of W. By equating the equations, that is the work done per cycle, and the work done per cycle means what is the differences that we are getting here, both are same. So WE is equals to 8000 into 3 by 2. So 12,000 Newton meter, what we are getting. We know that work done during the expansion stroke is 12,000 is equals to area of the triangle expansion stroke, that is A, B, C. And what is the excess? That is equals to ABC is the actual energy or work done during the expansion stroke. That is half into, it is just like a area calculation. So half into BH. So breadth into height. Half into breadth is the BC and height is the AG. So half into breadth is the pi into AG is the height. So AG is equals to T max is equals to 12,000 into 2 pi pi. That is 7638 into Newton meter. So and the mean turning moment diagram, that is equals to T mean. That is here more than the, we need to calculate the T mean. How much of T mean? So more than that, that is T mean, that is FG, work done per cycle by crank angle per cycle, that is 8000 by 4 pi. The total angle of crank angle is 4 pi. So total work done is 8000 by 4. That is 630. What is the excess? Now what is the excess? Excess is nothing but uh, T excess is equals to AF minus AF minus, or otherwise, what is the excess is AF. So AG minus FG, that is 7638 minus 637, that is 7001 Newton meter. Now from the similar triangles ADE and ABC, ADE and ABC both are similar. We can directly apply ADE by BC is equals to AG or AF by AG, or DE is equals to finally 2.88 radians. Then maximum fluctuation of energy delta E, actually uh, since the above area, since the above area, that means a mean turning moment line, which will represents the figure, it will represents the maximum fluctuation of energy. Therefore, maximum fluctuation of energy is equals to delta E. That is A triangle A D E. So for calculating that, half into DE into AF. By substituting all these values, we can get it 10,081 Newton meter. Let the I be the moment of inertia of the flywheel. We know that the maximum fluctuation of energy delta E is equals to I omega square into Cs. We know the delta E maximum fluctuation of energy, that is where it is the differences excess of energy is equals to I mass moment of inertia into omega. We know that the formula 31.42 whole square into Cs, coefficient of fluctuation of speed. That is just now we thought that about the 4%, it is 0.04. By calculating, by substituting all the values, we get I as 255.2 kg meters square. This is the finally what they required is moment of inertia I value and how much of excess energy is required. So this is the finally thing we need to find. Then one more problem. The turning moment diagram for a four-stroke engine, it may be assumed for simplicity to be represented by four triangles, the area of which from the line of zero pressure are as follows. During the suction stroke, the pressure value is 0.45 into 10 to the power of minus 3 meters square. Compression stroke 1.7 into 10 to the power of minus 3 meters square. Expansion stroke 6.8 into 10 to the power of minus 3 meters square. Exhaust stroke 0.65 into 10 to the power of minus 3 meters square. Each meter square area will represent 3 meganewton meter of energy. So for every meter square means 3 meganewton meter. Assume the resisting torque to be uniform and find the mass of the rim of the flywheel, which is required to keep the speed between 202 and 198 rpm, and the mean radius of the rim is 1.2 feet. So only here the question itself, we are having the pressure values, suction, compression, expansion, and exhaust. So here all the four things we need to substitute that for solving. In the previous problem, only compression and expansion strokes are the important things. And during suction and exhaust strokes, no work done was happened. So these are negligible, considered to be negligible. So what is the final thing is to be find out is find the mass of the rim. Find the mass of the rim to kept for 202 and 198 speed of the. So for what, how much of weight is to be required or how much of mass is to be required for a flight. Let given A1 with the pressure, that is a suction, A2, A3, A4. That is the pressures in the during the suction, compression, expansion, and exhaust strokes. And finally, the speeds have given only the very limited input, but only limited input, but high. That means a very vast thing we need to find out. Very important thing we need to find out. that is mass. That, and the second thing is the turning crank angle diagram for a four-stroke engine and the crank areas below the zero line of the thing of pressures has to be taken as negative, while the areas above the zero line of the pressure taken as positive. So the zero, as usually we have to take up the turning moment diagram. Horizontally it is a crank angle 0, pi, 2 pi, 3 pi, 4 pi, and vertical axis as torque, that is turning moment. The zeroth line more than it is the axis of x-axis. The below the terms we note it as negative, above the term we note it as positive. Therefore, we need to calculate that as finally from the figure we can see that A3 only A3 area is above the zeroth line, that is expansion stroke only. Then what about the A1, A2, A4? These are all below the zeroth line. So these are all negative and A3 only the positive. So from the figure, net area is equals to A3 minus of, that means A3 minus A1 minus A2 minus A4. So by calculating all the values, we get it that 4 into 10 to the power of minus 3 meters square. Since in the question itself the energy scale has given 1 meter square is equals to 3 mega newton. Mega means 10 to the power of 6 newton meter. Therefore, substitute that 4 into 10 to the power of minus 3 into 3 into 10 to the power of 6, that is 12 into 10 to the power of cube, that is 12,000 newton meter. Then we also know that the work done per cycle, that is T mean into 4 pi into Newton meter. These two from 1 and 2, we get T mean is equals to work done, where it is that F into G, that is equals to 12 into 10 to the cube by 4n, that is work done per cycle by crank angle per cycle. Okay, that is the formula. So 12 into work done, how much? 12 into 10 to the power of cube divided by total crank angle is 4 pi, that is equals to 955 Newton meter. And at the same time, work done during the expansion stroke, that is A3 into energy scale, which is equals to, for A3, how much of pressure? 6.8 into 10 to the power of minus 3 into energy scale that has given 3 mega Newton meter. So into 3 into 10 to the power of 6, that is finally 20.4 10 to the power of cube Newton meter. And also during the expansion stroke, the area of the triangle, how much of expansion stroke is, that is in the figure, the expansion stroke is ABC. Okay. So for the area, total area, expansion stroke, that is ABC, for finding the triangle area, half into BH, that is BC into H is nothing but the AG, half into BG or BC, that is pi. That means the difference is 2 pi to 3 pi. The difference is only the pi into AG. So half into pi, 3.1417, that is approximately 1.571 into AG. From the equation that previously we have taken the work done for expansion, that is 20.4 into 10 to the power of 3, and their work is done during the expansion stroke, both to be equal. So by calculating matching that, AZ is equal to 12,985 Newton meter. Excess torque. So mean T excess is equals to AF is equals to AG minus FG. That is equals to 12,985 minus. Previously we have taken the FG value 955. It's totally 12,030 Newton. Now from the similar triangles ADE and ABC, the same procedure what we have discussed in the first problem. Every problem is to be in the same procedure only. So for triangles ADE and ABC, with that by matching that DE by BC is equals to AF by AG, or DE is equals to AF by AG into BC. So by substituting that, we can get it the angle that is omega value that is 2.9 radian. Now, what is the maximum fluctuation of the energy that is delta is to be find out. Delta E is equals to area of ADE, that is maximum fluctuation. So half into DE into AF, that is equals to half into 2.9 into 12,030. With that, we can get it the excess. So finally, the mass of the ring, the mass of maximum fluctuation of energy is equals to pi square by 900 into m square r square into n into n1 minus n2. By getting that all the values, I get it m is equals to 1381 kgs. So the mass of the flywheel rim, mass of the rim of the flywheel is to be required for maintaining a speed difference of 202 and 198 is about 1381. That means 1380 Newton kg. 1381 kg. That is only the mass. If you need the weight means we can multiply with it 9.8. Okay, so approximately 13800. That means 13,800 newtons. Okay, with that the problems, some of the problems what we have covered now. So in the next class, we will discuss some more problems for the flywheel or turning moment diagrams and the flywheel for a punching press. Okay, thank you.